Hello, everybody, and welcome back to Math 105. Plan for today is we're going to finish off Standard 17 by talking kind of about the three classical problems we started last time and answer the question today of, is it possible to do these things? And then we're going to start Standard 18 and look at a new form of geometry that uses a system of postulates that's not quite the same as what Euclid used. I've got my usual office hours. Wednesday, 10 to 10:50 and from 2 to 3. Thursday from 10 to 11 and from 1:30 to 2:30. As far as homework goes, I mentioned this in the email, I think, but I decided to move the standard quiz due date from Wednesday this week to Friday. So Standard 16 and Standard 17 are both going to have quizzes that will be due at the end of the day on Friday. The reason I decided to move the Standard 16 quiz is with everything moving online and lots of people like leaving Hillsdale, moving around, etc. I just figured y'all are under a lot of you are under a lot of stress right now, myself included, so I thought I'd just give you a couple extra days to get to do that quiz, so you don't have to worry about getting it in by Wednesday night. Question. What does a mathematician choose when faced with a choice between ham, salad, and eternal bliss? Mathematician chooses ham salad because ham salad is better than nothing, and nothing is better than eternal bliss. Therefore, by the law of transitivity, ham salad has to be better than eternal bliss. Okay, so let's pick up where we left off from Monday's class. So Monday's class, we talked about each of the three problems that Euclid never proved you could do. First being trisecting any angle, given an angle, cutting it into three equally sized pieces. Second problem was doubling a cube. Given a cube, how can we make a new cube whose volume is twice the volume of the original cube? And finally, the problem of squaring a circle. Given a circle, how can we make a square that has the same area as the original circle? And I want to start off today by talking about the answer to the question. Can we show, using Euclid's starting axioms, his postulates, his common notions, his propositions, can we show that it is always all possible to do these three constructions? The answer to all three turns out to be no. Turns out all of these are not things that you can prove, that you can show that you can do using a straight edge and compass. In other words, using Euclid's postulates and his common notions. So, which is kind of interesting to me. And this is something mathematicians worked on, geometers worked on for thousands of years, trying to show how can we use the postulates and the propositions to show you can trisect an angle, double a cube, etc. Because after all, they're similar to things Euclid/Plato did show you could do, such as bisecting an angle, cutting an angle into two pieces. If we can cut it in two, why can't we cut it in three? If we can double a square, given a square, make a square whose area is double the original, why can't we double a cube? And before we move on to talk a little bit about why can't these three things be done, because it was proven relatively recently, in the 1800s in fact, that you can't do any of these three things, I want to talk about a couple of quick caveats to the statement of can these three things be done? The answer is no. So first of all, I'm going to pull up my notes here. It is possible to do some of these constructions if we can use tools other than what Euclid had. In other words, if you use postulates or common notions other than the 5 common notions and 5 postulates that Euclid himself used, it is possible to prove that you can do these 3 things. Just with the starting assumptions that Euclid had, you could not show that any of these 3 things is possible. So one example of something you could use, you can actually use techniques from origami, believe it or not. Japanese art of paper folding. You can actually use techniques from origami to show that you can trisect an angle. But in using origami, you're using things that Euclid himself did not use. I don't know when origami came into being, if it came after or before Euclid. I'm going to guess way after. You can use origami to actually help you trisect angles, but not using just the straight edge and compass constructions that Euclid himself did, based off of his postulates. Another note is just because we say things like, in general, you can't do this, doesn't mean there aren't some specific instances where you could. So, just to make a quick note, it is possible in some circumstances to do these constructions. For instance, there are some angles, like right angles, for instance, that it is possible to trisect using Euclid's methods. The problem is, the method that you would use to trisect a right angle only works for right angles. There's lots and lots of other angles out there that it is impossible to trisect using Euclid's methods. So we still say the answer to the question of can you prove that you can trisect an angle? The answer is no. It still works in some circumstances, just not in all circumstances. So for instance, you can trisect a 90-degree angle with Euclid's methods. But not, for instance, a 27-degree angle. 27-degree angle, there's no way to trisect. 90-degree angle, it is possible using Euclid's methods. And we're not going to get into how you would trisect a 90-degree angle because, in the interest of time, because it's a little bit of a complicated construction, but it is possible. So, now that I've kind of given some caveats here, I'd like to talk about a little bit about why we can't solve any of these classical problems. And the answer is related to this theorem. So, I haven't used the word theorem much yet in this class. Think of theorem as meaning the same thing as a proposition, something that can be proven. In this case, this theorem has a very, very horribly nasty, long, and complicated proof using stuff we haven't talked about in this class, so I'm not going to prove this theorem. But this theorem tells us some interesting things about what are the sorts of things that you can construct using Euclid's methods. It turns out that if you're given a line of length 1 unit to start with, 1 what, Dr. Gerstle? Doesn't matter. 1 foot, 1 inch, 1 meter, 1 mile. Just something, if you're given a line that has length 1, whatever that is to start with, then using Euclid's postulates and common notions, you can always construct new line segments that have any length as long as that length is either a counting number, so like you can use the line of length 1 to construct lines of length 2, 3, 4, 5, etc. A fraction of a counting number, meaning numbers like 2/3, 5/6, 11/9. You can construct lines whose lengths are these numbers. And also, you can construct line segments whose lengths are the square root of any counting number. Meaning, you can construct lines whose lengths are square root of 2, square root of 7, square root of 105, etc., etc. As long as you have a line of length 1 to start with, you can construct lines whose lengths are any of these forms. However, there are other lengths that you can't possibly construct using a line of length 1. And some examples of numbers like that would be numbers like cube roots, like cube root of 5, or fourth roots, fourth root of 9. Other numbers that you can't construct would be, say, something like pi. Pi isn't a counting number or a fraction of counting numbers, or the square root of a counting number. So given a line of length 1 to start with, it is impossible to construct a line of length pi. So let's do a quick example, though, before we go on to talking specifically about the classical problems. I want to do an example where we actually use a line of length 1 to construct a line whose length is square root of 3. Because it might not be that clear. How would you do that? How do we construct lines whose lengths are square roots of counting numbers? Where's my eraser? Here it is. This is going to be an example of how you would construct a line of length square root of 3 given a line of length 1. So if we're given this line to start with, and let's say we know that this line is 1 unit long, well, one thing we can do using postulate 2, the postulate that says we could take any line and extend its length to whatever we want it to be, we can use postulate 2 to make this line 1 unit longer and repeat that process to ultimately end up with a single line whose length is 3. This, by the way, would have to be how you would get a line whose length is any counting number. You just keep tacking on to your starting line of length 1 more lines of the same length of length 1. So we've taken the line of length 1 and tripled its length using postulate number 2. Next thing we're going to do is we're going to form a new line of length 1, this time at a right angle to the previous line of length 1. And what lets us do this? Proposition number 11. So we've used postulate number 2 to double the length of lines, and we can use proposition number 11 to say, given a line here of length 1, we can make a new line at a right angle to the previous line. That was part of proposition 11 said. Given a line, at some point on that line, you can make a new line going through that point that's at a right angle to the original line. And now we're going to triple the length of this line using postulate 2. And so we end up with a new vertical line whose length is also equal to 3. And now the next trick we're going to do, we're going to use postulate 1 to connect this point we started with here and the last point here with a straight line. And pretend that's a straight line. And here's my question. If this side is length 3, the bottom, and this right-hand side has length 3, what's going to be the length of the hypotenuse of the triangle we just constructed? Well, if this has a length of x, the Pythagorean Theorem, which is one of Euclid's propositions, is going to tell us that 3 squared plus 3 squared has to be equal to x squared. Well, that's going to then tell us that 9 plus 9 is equal to x squared. Hold on, I just realized something. 3 squared plus 3 squared. That's not square root of 3. I screwed something up. Change of plan. We're going to start with the line of square. We're going to construct a line of length square root of 18. Because here, when I solve this equation for x, I'm going to get x squared is 18. And so what I end up with here is just a line that we've constructed from this original line, whose length was 1, where this new line is going to have a length of square root of 18. Which, if you prefer, you could also write out as being equal to 3 times the square root of 2. So this would be how we could construct a line whose length is equal to square root of 18, just from starting with a line of length 1, using propositions we've already discussed, and except for the Pythagorean Theorem, propositions we've already proven. So let's try and answer the question now of why can't we solve any of these classical problems? The answer is going to come about from this theorem. So let's, for instance, try and solve the question of why can't we double a cube? So let's say we started with a cube whose sides are all of the length 1. Remember, cube means all side lengths are the same. So we have a width of 1, a height of 1, and a length of 1 unit. So what would the volume of this cube be then? Well, the volume of this cube would have to be equal to 1 cubed, which is just 1 unit. So we're starting with a cube of 1 unit, and we'd like to ask the question of, can we possibly construct a cube whose volume is 2 units? Two by 2 by 2. Or not 2 by 2 by 2. Blah, blah, blah. Well, if we were trying to construct a cube whose volume is 2 units, then that would correspond to having to construct a cube using line segments whose length is some number x. Remember, if this is a cube, the width, length, and height would all have to be the same. And so, what would the length of each of these sides be of our new cube whose volume is double the volume of the original cube? Well, let's take a look. In order for the volume of this cube to be equal to 2, that would mean that x cubed would have to be equal to 2, because the volume of whatever this cube is would be width times length times height, which, if those are all x, that'd be taking x times x times x, which would then just give us x cubed. So if x cubed is equal to 2, what would x have to be? Well, x would have to be equal to the cube root of 2. So in order to construct, or in order to double our cube whose sides are length 1, we need to make a cube whose sides are all length cube root of 2. Is that possible? Given a cube, given a bunch of lines of length 1, can we construct a cube using lines whose lengths are equal to cube root of 2? Well, according to this theorem, no, you can't. Cube root of 2 is not a counting number. It's not a fraction of counting numbers. And it's not a square root of a counting number. It's the cube root of a counting number. It's the cube root of 2 specifically. But it's not any of these things. So according to this theorem, we can't construct lines of length cube root of 2, meaning we can't possibly construct a cube whose volume was double the volume of the original cube. And that's why doubling a cube is impossible. Because in order to double a cube, you need to be able to construct line segments whose lengths are not any of these three things. I'm not going to go through the arguments for why he can't trisect an angle or squaring a circle, but it ends up being very similar. In that, in order to be able to trisect an angle or to square a circle, you would need to ultimately be able to construct line segments whose lengths are none of these three things, which according to this theorem, you can't do. Okay, that's going to do it for standard 17. Standard 17 showing that we can't do these things that we could do nicely back in standard 16. We could bisect an angle, we could double a square, but in standard 17, we showed that we can't trisect an angle or double a cube or square a circle, which didn't have a nice standard 16 analog to it. So next thing I want to talk about is standard 18. Give me a second to erase the board here. Standard 18 through 20, the last three standards, are all going to have a very similar theme to them. And that these last three standards are all going to be based around the idea of what did modern geometers do differently than what Euclid did. So let's erase this, give myself some working room. So everything that we've been doing so far for the last several standards, I would refer to as being called Euclidean geometry. Because we're trying to do geometry, play around with lines and circles and angles and other shapes, using Euclid's tools. Using Euclid's postulates, Euclid's common notions, doing Euclid's propositions. All the geometry we've been discussing is heavily related to things that Euclid himself did. And in the last three standards, we're going to do something a little bit different in that we're going to look at systems of geometry that were not what Euclid did. On this side. So standard 18 is going to be about a new system of geometry that wasn't what Euclid did, called elliptic geometry. So I'm in the standard 18 packet now. And the whole idea behind these two other systems of geometry, elliptic geometry in this packet and hyperbolic geometry in standard 19, is we're going to do a postulate that's different from Euclid's fifth postulate, the parallel postulate. If you recall, Euclid's version of the parallel postulate which I'm going to refer to as the Euclidean parallel postulate, had two different versions. Euclid's version, which said something about if you have two lines and a line going between them, and if the angles on one side add up to less than two right angles, then the lines are going to have to intersect. The version I'm going to choose to write down is the more modern version, which, if you recall, the modern version of Euclid's postulate 5 is the one that says for every line L and every point P not on L, there exists a unique line M through P that's parallel to L. So in other words, if we're given a line L to start with, say a line that looks something like this, and if we're given some point P way down here, according to this postulate, there's exactly one line, M, that both passes through the point P and that is also parallel to L. Parallel meaning the L and M do not intersect at all. And this was the modern version of Euclid's fifth postulate, which we said was logically equivalent. And if you recall, we said back in standard, which standard would this have been? Standard 12, we said that this is a very controversial postulate. One that a lot of mathematicians, a lot of geometers were not fans of, because this felt to them like something that needed to be proved, like a non-intuitively obvious statement, as opposed to something that we can just assume as a postulate. And so I know I mentioned to you that for a very long time, a lot of geometers were interested in trying to see, can we prove the fifth postulate from the other four? Where the answer was no. But there also have been a lot of other geometers that have said, I don't like the fifth postulate. What if instead of Euclid's fifth postulate, we had a different postulate that said something different? And what sorts of geometric mischief could we get into if we replaced Euclid's parallel postulate with a different parallel postulate? And in doing so, that's led to some new forms of geometry other than what Euclid is studying, including what we're going to be talking about in this standard, which is the idea of elliptic geometry. So, elliptic geometry is going to be sort of an umbrella of term used to describe a bunch of different systems of geometry. And it's going to be a system of geometry where Euclid's fifth postulate where the Euclid's parallel postulate has been replaced with a new parallel postulate. And this new parallel postulate is going to be called the elliptic parallel postulate. Where what this postulate says is that given any two lines, L and M cannot be parallel. In other words, no parallel lines do not exist. I know what some of you are thinking right now. Dr. Gersel, what do you mean geometers replace the Euclid's parallel postulate with this one? Given any two lines L and M cannot be parallel. That just sounds stupid. Why would you assume that? Parallel lines can totally exist. Here's an example of lines L and M. Boom, lines L and M that do exist. In your face, elliptic version. Well, that's certainly true. Using Euclid's definition of lines, or in this case, the modern version definition of lines as being things that go off in both directions forever without changing direction, it certainly appears to be the case that the elliptic parallel postulate is a little bit silly. This can't be true. that's assuming we're using the same definition of lines. What if we had a different definition of lines where lines behaved in different ways? And in doing so, we're creating new ways of looking at geometry other than the flat two-dimensional geometry we've been discussing so far. In particular, what I want to do now is I want to define a new way of looking at geometry, new definitions for lines, in which the elliptic parallel postulate is suddenly going to become true, whereas the old version, the Euclidean parallel postulate, will no longer be true. And in doing so, we're going to construct a version of geometry, kind of a specific sub-branch of elliptic geometry, called spherical geometry, where we're doing geometry, instead of on a flat two-dimensional surface, on the surface of a sphere. So let's draw that out and see what that looks like. So here we're going to be doing spherical geometry. Where spherical geometry is just going to be a branch of elliptic geometry. Where all the points we're going to be looking at are points on the surface of some sphere, like the surface of the Earth, for instance. And lines in this system of geometry aren't going to be things that look like this anymore. That doesn't make sense. A line can't extend out forever if it's trapped on the surface of a sphere. Sphere has a finite surface area to it. The line eventually would have to end. So here, we're going to define lines to be great circles on the surface of the sphere. Lines are defined to be great circles on the surface of the sphere. So to draw something like this, where we draw a circle going around the front of the sphere and then looping back around to the back. Dotted line means it's looping back around the back side of the sphere. We can't see it unless we're using X-ray vision. I'm just drawing it out as a dotted line so you know what's going on. Pretend like you can't actually see it. But if we were to draw a circle starting at this point here on the surface of the sphere that goes all the way over here and loops back around, that is going to be something that we will now call a line. Here's another example of a line. Something that starts maybe at this point here, goes down to here, and loops back around. And here we have yet another example of a line on the sphere, a great circle on the surface of the sphere. So Dr. Gerstle, what do you mean when you say a great circle? By a great circle, I just mean a circle that encloses the maximum possible area. So what that means is technically I could draw a line going around the surface of the sphere that does something like this. Just like a little line that kind of overlaps just a tiny, teeny bit of the sphere. But if you look at the circle that's kind of trapped inside of this line here, that's a tiny, small circle. It's not very big. It's not the biggest that it can possibly be. Whereas this circle that I drew right here and this circle that I drew right here would be examples of lines on the surface of the sphere where the circles kind of trapped inside of this great circle can't possibly be any bigger. I can't make this line extend it out any longer. If I did, it would no longer be on the surface of the sphere. And ditto for this one that I drew right here. Wouldn't be on the surface of the sphere anymore. Wouldn't be a great, so it can't be made any bigger. Thus, these are going to be defined to be our new lines on the surface of the sphere. And if you notice, and this is something that's really cool, I can try all day long to draw great circles on the surface of the sphere, but I'm never going to be able to draw one that doesn't intersect the other great circles. So for instance, let's say I had this great circle to start with on the surface of the sphere. Let's see if I can draw another great circle of maximum possible area that doesn't intersect this one. I'm going to draw one that starts here. It has to be a big possible area. Oh, shoot. I've already intersected. Okay, fine. How about this circle? Yeah, that one didn't intersect this one. Oh, wait. This isn't a great circle. This doesn't count as a line. All right. How about a great circle starting here? Shoot. The great circle intersected both of the great circles that we already had. It is literally impossible to have two great circles on the sphere that don't intersect each other. Any two great circles we draw will always intersect each other at some point. Say in this case here, or here, or here. It's impossible to have two great circles not intersecting. And since our lines are defined to be these great circles, we're saying I'm going to choose to define the word line in such a way that these are our only lines. What that means is that parallel lines do not exist in this way of looking at geometry. Given any two great lines, meaning any two great circles on the surface of the sphere, those two lines / great circles must intersect with each other. And so, while this model of spherical geometry doesn't satisfy the Euclidean parallel property, the Euclidean parallel postulate, meaning the postulate that Euclid himself proposed, or its modern version, this definition of lines as being great circles on a sphere is going to satisfy the elliptic parallel postulate. So let's write that down. I'll draw a little sphere so it's off to the side. This way of looking at geometry is going to make the Euclidean parallel property postulate false. But the elliptic parallel postulate true. And what that tells us is spherical geometry is a branch of elliptic geometry. It's a way of looking at geometry where suddenly we have the elliptic parallel postulate being true instead of the Euclidean version. And this has all come about from geometers trying to play around with geometry and notice things and say, I don't like Euclid's parallel postulate, the fifth postulate. What happens if we get rid of it? Because here's a cool thing. While the spherical geometry doesn't satisfy Euclid's fifth postulate, it does satisfy the other four. All right angles are still equal given any two points. You could still find a unique line between them. In this case, the unique line between these 2 points would be a great circle that looks something like this. So postulate 1 still works. Given any line, you can make it longer. You can change its length. Technically, postulate 2 no longer makes sense to say because all lines are always the same length. So line can be continuously extended does no longer make sense to talk about. What's a circle? Well, circles don't really make sense to talk about in elliptic geometry either. So the third postulate doesn't really make sense. But the fourth postulate still works. The first postulate still works. We've now created a system of, okay, I lied earlier when I said the first 4 postulates all still work. But the first and fourth postulates still do work, and now we have a different postulate in place, the elliptic parallel postulate, that's different than the one Euclid had for his own system of geometry. And so, in an effort to get rid of Euclid's parallel postulate, geometers, in turn, were able to find other ways of looking at geometry like this, new ways to define things like lines and angles and circles in ways that made geometry work differently. So, before I leave you for today, let's look at one way in which elliptic geometry is different from regular Euclidean geometry. In particular, I'm going to look at a proposition of Euclid's that is true in Euclidean geometry, maybe not so much true when it comes time to looking at elliptic geometry. And that's going to be Euclid's proposition 32. So Euclid's proposition 32 is one of Euclid's sort of key proposition, or I keep saying not postulate 32, proposition 32. Euclid's proposition 32 is one of those propositions where it's sort of a two-pack, where Euclid is making two different statements in the same proposition. Sort of like how angle side angle and angle angle side were kind of lumped together in the same proposition. But what the second part of Euclid's proposition 32 said is that the sum of the three interior angles in any triangle is equal to 2 right angles. So what that means is that if we're looking at one of Euclid's triangles, let's say this is point A, this point B, this point C. If we were to try and add the size of angle A in degrees, plus the size of angle B in degrees, plus the size of angle C in degrees, according to Euclid, these three angles, when summed together, how big they are, should give us the same size as 2 right angles. Which, if a right angle is 90 degrees, and if we're doubling that, that's giving us 180 degrees. So in other words, it's one of Euclid's propositions, something that Euclid was able to prove, that if you take any triangle, the way Euclid understands them, using Euclid's definition of lines, given any triangle, the angles in that triangle, will always sum to exactly 180 degrees. Let's see if that's going to be true in elliptic geometry. And in particular, let's look at in spherical geometry. Well, I'm going to draw a sphere and draw a triangle on that sphere. So here's one great circle. Let's draw 2 more great circles that pass through this point up here, which I'll call A. Let's draw a line going from point A to point B. And a line going from point A to this point here, which will be point C. And I claim this is going to be a triangle. We have a line going from A through B, from B through C, and from C through A, all three of which are great circles. So, what's going to be the angle sum in this triangle? Well, if you notice something, this angle right here, the line going through B here is going from left to right, whereas the line from A is going straight up and down through B. Think about these great circles as being like latitude and longitude lines. Where here, the line going from A through B is going from straight north through south, whereas the line going from B through C is going from straight east to west. So this line here is actually, these two lines are going to be perpendicular, meaning the angle at B is going to be a right angle. How about the angle at C? Well, the line going from A through C, think of it as being like a longitude line on a sphere, is going straight north to south. Whereas again, this is like a latitude line, like the equator, the line going through B and C, is going straight east to west. So what's that angle going to be? Well, these lines are perpendicular. That is also a right angle. So if we were to take the angle at A, add it to the angle at B, see what that gives in degrees, add that to the angle at C, well, that's going to be whatever angle A is, plus 90 degrees, plus 90 degrees. That's not, angle A, it's not very big, but it's greater than 0. This is going to be greater than 180 degrees. And that is going to be something that will happen anytime you're looking at triangles in elliptic geometry. In elliptic geometry, triangle angle sums will always be greater than 180 degrees. Gadzooks. Also something to notice is all triangles in Euclidean geometry are the exact same. They're always exactly 180 degrees. But in elliptic geometry, you can have two triangles in the same model, like in spherical geometry, where the angle sums are different. For instance, if I drew a point D out here and a point E out here, and then drew these great circles, angles at D and E would still be right angles, but the angle from D to A to E would be a lot bigger than the angle from B to A to C, because D to A to E is much bigger. So the triangle angle sum and triangle ADE is greater than the one than the angle sum in the triangle ABC. In elliptic geometry, it's totally possible to have two different triangles whose angles sum to something different. They're always going to sum to things greater than 180 degrees, but they can be different. Maybe ABC sums to, 200 degrees, while ADE sums to 215 degrees. Whereas in Euclidean geometry, in the way of geometry we've been doing all semester now, with this definition of lines, the triangle angle sum will always be the same. No matter which two triangles you look at, they will always sum to exactly 180 degrees. And that's where we're going to leave things off for today. So today we looked at kind of what lines and angles, etc. look like in a new way of looking at geometry. We showed that proposition 32 is true in Euclidean, but not in elliptic geometry. And the next class, we'll talk a little bit more about elliptic geometry and look at some more properties that work in Euclid's geometry, but not on the surface of a sphere. Hope you're all doing okay. Hope you're all staying healthy. Please let me know if there's anything I can do to help you, for real. And I'll talk to you later. Have a good one.